Hey, okay. All right, so first of all, here's what I want to talk about today. Let's do a quick review of some of the properties about antiderivatives. This is stuff we did before spring break. Then after, what we're going to do today is we're going to get to our new stuff, which is acceleration, velocity, and positional vectors for... So I want to get to the antiderivatives for acceleration, velocity, and position. And then we'll do a couple examples. So I got about 3 or 4 examples I'd like to cover today. Just kind of a range of topics here. So first of all, let's talk about the natural numbers here and antiderivatives. Okay. All right. First of all, if we do an antiderivative of e to the x, the antiderivative to it is just e to the x.
Lord, hit us with the
No. So, okay. So, hey, antiderivative of e to the x is e to the x because here's how you think of it. If I'm going to take the derivative of this object, would it get me back to the original? Yes. Yeah. So, that's the idea. Okay, so if I take the derivative of e to the x, it would get me back to the x. That's how I know if I did it right. If you take the derivative and you're back to the original. Now, the other one that we talked about before break, we talked about 1 over x. I think this is one of our homework questions we had. Yeah. The antiderivative to this is natural log of x plus c.
You didn't give us homework over break, did you?
No. Okay. So that was something we had before break. It was one of the examples we did.
It was a homework.
So the antiderivative of 1 over x is ln of x, because when you take the derivative of this object, when you take the derivative of this, derivative of natural log is just 1 over whatever's in the parenthesis times the derivative of the parenthesis. So it'd be 1 over whatever's in there times the derivative inside. Then what we also talked about is we talked about the trig functions. So like if we did, let's say, cosine of x dx, and we're finding the antiderivative of this. The antiderivative of this is sine of x. Yeah. Because if you take the derivative of sine, like the normal derivative of sine, you'd be back to cosine. That's the normal derivative of sine, is cosine. Then what we also talked about was the if there was a sine here. Now this is the only one that was kind of odd. The antiderivative of sine is negative cosine. It's negative cosine because the derivative of cosine would be negative sine. But then what I need to do is put another negative in front of it to change it to positive. That's why this has to have a negative sign out front. The derivative of cosine is negative sine, but having a double negative would make it positive. So that's the idea. And then I think the other one we had was, I think, secant squared. Secant squared. So 1 over, or sorry, just, yeah, or 1 over cosine squared. Secant squared is just tangent. And then these are all plus c's on the back. I didn't put those. All right. Questions with all the specific antiderivatives that we had before spring break?
Not yet.
Okay, these are the ones we talked about. We also did a bunch just normal power rule. Just all the regular stuff that we did where you add 1 to the power, divide by whatever the power turns into. Those are the normal things. If you have a derivative of a constant, so let's say we take the antiderivative of a constant, let's say like 10. This would just be 10x, right? And then it would be plus c as well, because you add 1 to the power and you divide by what the power is, right? That's how it works. So adding, because this is technically x to the 0, you add 1 to it, so it makes it x to the first. So that's the idea. All right, questions on the antiderivative stuff?
That was review, right?
Yeah, all review stuff. Okay, well, hopefully you can kind of memorize it then.
And then you didn't pay for it. They remember this, right? I was gone. I like the rainbow you made. I think you
Yeah. Okay, we're good? All right, let's...
This was your fun during break, and you never actually taught us it.
What?
This is what you did for fun. That's what you did for fun.
No. All right, let's talk about the new stuff today. So we have brand new stuff. This stuff we have not discussed yet. I just want to make sure that you guys get to see this for the first time today. Today is an intro day. It's nothing like we're not getting anything like super difficult. I just want to show you what we're going into. This is the new section 6.2, if you will. We have a couple sections left of chapter 6 here. Here's how I want you to think of this. So this quarter, we have 45 days. It's technically 40 for you guys or something like that, 42. For you guys that are left, how this works is about every 15 days we're going to take a test in here. So that's a rough like time. So how that works, we have to finish chapter 6 here. Obviously, we have a couple sections left, 2 or 3. Then we'll take a quiz, test, whatever you want to call it. Then we'll do another unit, which is on matrices and logarithms one more time. We'll take a unit test over that. Then we'll prepare for a semester test. Your semester test for you guys will be the Monday and Tuesday, the last week I have you. You're out on like a Wednesday. I don't know, what is that?
You get out in the middle of the week?
Yeah, you're out. You're like your last day is a Wednesday, so you'll take your semester test Monday and Tuesday. Wednesday of that week, you'll check in your books and stuff.
Ward.
What?
So I was just doing it's basically calculus this morning.
Okay.
And I figured out how much percent of school we got left, and we got 1.9% of our 13 years left.
Ooh, that's a weird way to think of it. I thought you had a quarter left. But overall, it's 1.9.
Big math. Big math.
I appreciate that number. All right, moving on. Okay, yeah, all right, probably not. Just moving on. All right. Okay, all right.
That's as far as math should go.
All right. So let's get to the new stuff today. Here's the numbers I need you to write. All right. So in terms of gravity, 9.8 meters per second squared.
Wait, really fast before you get into too much, is trigonometry equivalent to calculus or pre-calc?
Pre-calc.
Why does that?
All right, next.
Secant squared or second?
Seconds. Almost got me. All right, 32 feet per second squared. Okay.
It also equals that.
These are the same numbers. The only reason why I have these, they're in terms of label, like meters versus feet. If you need to change them, it's just a quick conversion. These are the two numbers you basically need for this section. If you can get these two numbers memorized, the problems are going to be really straightforward. What this represents acceleration of an object. Let's see. Acceleration? I don't know. Is that how you spell it? It just seems wrong. It seems wrong, the acceleration word. Man, my spelling is so bad, I don't even know how to spell acceleration. All right, good. All right. We'll go with that. All right.
I swear, I'm Grammarly.
Okay. Hey, we got some stuff to cover today, and you guys are kind of wasting my time right now. So, let's talk about what we're going to be covering. So, the examples we're going to be going into will be something like, let's say that you're on top of a building, and you're going to drop an object off it, like let's say like a shoe off the top of the building. And what I want to know is what the speed will be by the time it hits the ground and what time it will take for it to actually touch the ground. Okay, so yeah, it's a lot like physics. When you see it, you'll actually understand where the physics formulas come from. So that's the beauty of this. So so if you've taken physics, this will seem super easy. Okay, so here's the idea. So let's say you're on a 50-foot building. Okay, 50-foot building. Okay, and you're gonna just let it go and let the object fall. Okay, so and I want to know what time it will hit and what the speed will hit when it touches the ground. So for the first time anyway. So now here's the idea. Obviously, since this problem's in feet, like I'm giving you that number to start with, I'm going to be using this acceleration formula because it tells me by just seeing the label in feet, I'm using 32 feet per second squared. Okay? All right, does that make sense, like how I can identify which number I'm using? Okay, so now.
It's about a second of that.
Okay, let's talk about that. So, acceleration is 32 feet per second. Now, how this works is that since this number is going towards the ground, it's negative 32 feet per second. If it was going up in the air, that's positive. Gravity is pulling down. Downwards is shown by negative numbers. Positive is showing by going upwards. Okay, so just keep that in mind. Upwards is positive, downwards is negative. And so this is my acceleration formula. If I want to find velocity, all you have...
Acceleration isn't going to be negative.
So it's negative. It's pulling it towards the ground.
No, it's speeding up, so it's
No. So all the positive negative tells you is if it's going up or down. That's all it tells you. It doesn't tell if it's speeding up or slowing down.
Okay, but negative acceleration is deceleration.
In terms of like physics, I'm talking about like positional ways, like whether it's going up versus down.
Okay.
Yeah, I understand what you're saying though. I understand what you're saying. Now, for velocity, all we have to do for 32 feet per second is take the antiderivative to that. Antiderivative. So it's 32x plus c. That's the antiderivative, right? You add an x, you add a plus c, that's the antiderivative. That would be the velocity formula. Now, what we have to do is plug in our positional. So what was my initial velocity when I let go? 0. So this number here is 0. That was my initial velocity when I let go. Now, if I was throwing it towards the ground, you'd have a negative velocity because it's heading towards the ground. If I threw it up in the air, I put a plus to show that I'm throwing it up in the air. Because sometimes, like if you're going to launch like a rock, right, you're going to throw it up in the air. That's a positive velocity. It's going up. Negative would show it's going down. So that's the positive 0. I'm letting it go, and it's just flat. Okay. Then I'm going to do an antiderivative again. And what this will give me, when I do the antiderivative one more time, this will be the positional vector, what they call distance. So this will be 32x squared over 2 plus 0x plus c, right? Because you always add an x to the...
Once you put that over 1?
And yeah, it's over 1. So, oh, sorry. Didn't even realize I was too far down. All right. So now, at this point, now what I have to do is plug in at time, or at position 0, what was my height off the ground?
50 feet.
50 feet. So that would be this number right here. Because at time 0, x represents time.
It's x squared over 2 because you're adding 1 and then dividing by 9.
Yep, you're adding, that's how the antiderivatives work, right? So, and this would be 0x. Now, if you want to simplify that to make that like negative 16x squared, that's fine. You can do that too. All right. Does this make sense what we just did?
Sure.
Now, what x represents... No, that's fine. I'm not going any further here. What x is going to represent, though, is going to represent time. That's all it is. That's all x represents for me. Okay. So, any questions with the start of this problem?
Only hope.
Okay. Now, to solve this out, to figure out my time, my x, here's what you do. You just set this equal to 0. You set this equal to 0 for my distance of 0, and this will tell me what the time it will take to hit the ground. D is the height, right? The height off the ground. So if I want to figure out when it's like 15 feet off the ground or 20 feet, I put that number over here. I want to figure out when it's going to hit the ground, 0 feet off the ground, when it's going to finally touch. And so that's what my distance represents. To solve, you'd subtract the 50 across. I'm going to simplify these numbers a little bit. Right? So 32 divided by 2. Divide by the 16. Negative 16 anyway. And then take the square root. And this will give me the actual time. And this will be plus or minus. This will give me plus or minus the time it would take for me to, for that object to hit the ground. So now, square root of 50 over 16. In terms of just number, if I type that in, 50 divided by 16, close the parenthesis. Say it again. Yeah. So it's 1.7677, and that's in terms of seconds. Now, why it's in seconds is because the original problem was in seconds. So feet per second, right? So it's going to take 1.7 plus or minus. Now, obviously, negative time won't make any sense. So positive time, so 1.76 seconds from now, the object that we dropped the shoe in this case hits the ground.
Test this out.
Okay. That's fine. We can put it to a test or something like that, right? Now, here's the idea. This is considering. I'm not even considering weight of the object. I'm not considering anything. Because gravity affects everything differently, like a feather, obviously it would catch, this is in terms of like, thinking about like like zero air resistance, not like a wind or anything like that. It's just maybe in a vacuum, like hits the ground, right? So So about 1.76 seconds, so almost 2 seconds. Now, here's the idea. If I want to find velocity, all we have to do is use this number that we just found and plug that in up here into my velocity formula. Because velocity will tell me the speed that it's actually going to hit at. And it'll be negative because it's going down towards the ground, so which is fine. So I'm going to take my velocity formula, which is that negative 32x plus 0, and I'm plugging in my x number, which I just found is 1.76 seconds. 1.7677 seconds plus 0, right? Which I don't need the plus 0. And this will give me the velocity that the shoe would actually be reaching once it hits the ground. Now, obviously, at some point, it's going to hit terminal velocity. That's like the maximum speed an object can hit. But this would account for just the generic things like certain heights. So, question.
So in a vacuum, 10 pounds of styrofoam would hit the ball, or it would hit the ground at the same time as a 10-pound bowling ball.
Yeah, if they weigh the same. Yeah, they hit at the same time. Same with like a feather. If a feather weighs the same as like a piece of paper, like if they weigh the same, they hit the same time in a vacuum. So the only thing that holds a feather is that air resistance. That's the
So
only
does the feather like, is it like round? Did it on vacuum or is it just straight?
straight down. Just hits like it was like just weight basically. Yeah, they have videos of it online if you want to watch it. YouTube videos.
Oh, you see, how you throw something up, it comes down, it's the same velocity as when you let go of it?
Yeah.
So really, if I was like standing over the Grand Canyon and I saw something at the bottom and I wanted to hit it really hard, I could throw it, it hit at the same speed if I chucked it straight down or if I chucked it in the air and then it came down, right?
I think what would come down to, in that point, it would come down to just timing, like how far it's going to go. Because you throwing it down, if it reaches terminal velocity anyway, it's going to hit at the same time. Because the height will depend, right?
Yeah, but
So-
say it didn't hit terminal velocity.
Then yeah, if you threw it the same, it would be
more efficient.
Yeah, it'd be more
You'd
efficient.
use less
so.
energy going up because air resistance going up. So it'd be a fraction of the energy, but you'd be a little bit harder.
It'd be
structure.
really close. It'd be close. I would.
See, the only thing, I wasn't doing any of this. I was doing thought experiment.
Yeah.
And then I was thinking, the only thing that should, no, I wrote this, but the only thing that should mess with it is if I gotta throw it at an angle, because the same thing's over here. I only gotta account for the angle of it one time if I throw it down, but it's like twice if I throw it in the air. But I guess it's half the angle, so it should be the same.
Just don't think about it, Isaac. Just do it. Nike. Just do it.
Just do it.
That's why they tell you.
Good question. Good question.
They say if you throw a penny off the Empire State Building, you can kill someone walking down.
Yeah, it can
You
crack.
tried
It
it, didn't
can
you?
it can crack, Matt.
Yeah, I did. I threw a freaking quarter off the Empire State Building.
Yeah, you could crack cement at the bottom. That's why they have those balconies that you can't see from the top. It'll never actually reach.
Okay, wait, I did do worse than that in Florida.
Ugh.
So I had a
Alright.
cutie, right? You know those little oranges?
Yes.
Right? 10th floor balcony, boosh. Lady down on the floor.
That probably hit her like a brick.
Probably hurt.
So they say like a coconut, like 30 feet off the ground will hit with a velocity of like 2 metric tons. That's 32 feet off, and that's a coconut, right?
Coconut water is dog.
I don't But anyways, an orange, and you whipping it,
I ripped that thing.
you probably could have gave her a skull fracture.
I didn't give her a skull fracture. It didn't hit her in the skull. It hit her in the shoulder. Rotator cuff gone.
All right, anyway. All right, so.
I wasn't trying to hit someone. I was trying to hit the pool and like splash and make the little kid scared,
Oh
you know?
my goodness. All right. Well, anyways, other than assault, let's go on to the next part. All right. So,
I ran so
'kay.
fast back into my room. Oh my goodness.
all right. So, let's move on. All right. So, the number I heard earlier, 56 feet per second. We're hitting it pretty fast speed.
We're going flat.
Yeah, we're going quick. Now, here's the idea. What this does, and you probably recognized it when we looked at these formulas. This formula right here, this is what they teach in physics for velocity and distance, right? They teach this formula where it's like, it's your velocity, or it's gravity, divided by 2, and then it's your initial velocity, x, plus your position. Like, you plug in those 3 numbers in physics.
I just don't think Morgan remembers.
So these are the numbers they teach. Again, this is gravity. This is the initial velocity that you released it at. This is the position. And that in physics, they just teach you to plug in those numbers and you're done, right? They just tell you what to plug in where. For what we're doing in calc, you actually develop the formula as you go, and it makes sense why it turns out the way that it does. It's reverse engineering antiderivatives as you go down, and it just slowly makes the formula as we go. Kind of a cool concept. Let's do one more. Hey, shh. Let's do one more. There's one problem I want to actually figure out in the book. They had one homework problem I actually want to know the answer is. So, all right, here we go.
Okay, wait, more. Can I just look up how much force?
Okay. Shh.
Oh,
Hey.
I haven't seen your picture, so
Hey, let's go.
Orange is about the size of a baseball.
they still love sure.
They don't weigh the same. A little smaller.
Smaller.
Okay.
Mine's
Hey.
horrible, like, I'm gonna cry.
Hey, can we finish up here? I got one last problem here.
And then I got so upset.
Okay. All right. So rock. We're gonna throw a rock downwards. We're gonna throw a rock downwards at a velocity. So here's my rock. We're gonna throw it down with the velocity of 10 feet per second.
Nice.
So this is the velocity, initial velocity. We are going to be 100 feet off the ground.
Oh God.
So this is the initial distance off the ground, the height. Maybe I'll put height instead of a distance. So.
Control your eyebrows.
Okay. All right. So now here's the idea. What I want to know is what time will it hit the ground, and what's the velocity when it actually reaches. So it's got the same two problems. So this one actually has an initial velocity. It's being thrown downwards, not up. So we're going to have that initial velocity will be a negative number, that plus c number. So the good news is on this one, we're still going to use the same formula as we did the last one. So I kind of left it up here just so you can see it. So, all right. So let me.
We're going up. We're throwing the rock up.
So.
No.
No, we're throwing downwards. We're throwing it downwards
Why
initially.
is the feet per second positive?
We're not. I'm gonna throw a negative number in there when we get there.
Square that baby, or
So.
it'll be too easy.
All right, so here we go. So plug in my numbers here. So my acceleration is negative 32 feet per second squared.
Is that 10 feet per second squared or no?
No, that's just the velocity. So that's feet
That's the
per
speed.
second. That's speed,
Oh,
not
that's speed. Let it
acceleration.
go.
Yeah. Okay. All right. So we got my acceleration is negative 32 feet per second. We do the antiderivative to this, which turns out to be the velocity formula. That's the antiderivative of acceleration. So that's negative 32x plus c. Now, my initial plus c is that initial velocity I released at, and you guys even said it. It was negative 10 feet per second. So that's that number right there. There's the formula with my negative
Why
10
did you
plugged
change
in.
it to line?
Because it was going down. I just showed this arrow earlier as down, so I had to make it negative.
Okay.
Down is showing that it's going towards the ground. Positive, if I want to throw up, I put a plus 10.
I just yeah,
Okay?
there.
Does that make sense?
Happy.
Okay, all right. So now we do the antiderivative again, and this will give us
This
distance. So this is negative 32x squared over 2 minus 10x. And now my initial height is 100 feet off the ground. So that's my plus 0. That's the plus c in the back. All right, so now what we need to do is figure out the time. Once I have time, I can go plug it back into velocity, and that will give me, the velocity that's hitting the ground at. And we can see the difference here. So obviously it's going to be a little bit faster once it hits the ground. So plug in my numbers here. So this is negative 16x squared minus 10x plus 100. That's simplifying this out a little bit.
equals 0.
And yeah, we're going to set it equal to 0 and just do the, we could factor this thing apart. I think I'm just going to do the quadratic formula on this one because we have all three numbers. So the quadratic formula, negative b plus or minus square root b squared minus 4 times a times c.
Why are we doing this?
This is to figure out my x, my time.
We're doing some factoring.
Yeah, instead of factoring, because I need to factor that thing apart, I'll just do the quadratic formula instead of factoring, because I don't think that thing's factorable.
All over to
And then 2 times a, which is negative 16, right?
Said that right when I thought it.
Okay. All right. So plug in the number here. What do we have? We have 10 plus or minus. This is 100 minus or plus 6,400. So that's 6,500 in there. All over negative 32.
500. Oh, never mind. Not gonna question?
That's, I think it was right, 4 times 16 times 100. Is that right?
Plus 100.
Plus 100, yeah.
Yeah.
Yeah, that was right.
Divided by 32.
Negative 32, yep. So, all right, so the number we're going to use here, we can either use 10 plus the square root of 6,500 divided by negative 32, or we can use 10 minus the square root of 6,500
Let's use.
and divide by negative 32. I think we're going to use this one. The reason why is I needed this number to turn out to be positive.
32 either way.
Yeah, but one of them's, the negative 32 is on the bottom. But the thing is, it's positive or negative. I think we have to use the second one because I need this number, this x, to turn out to be positive. So 10 minus the square root of 6,500, that's negative 70, and then I'm going to divide by the negative 32. So this ends up being this number back here.
Scroll down.
8.
Oops, sorry. Is it? Oh, yeah. Sorry. So this ends up being 2.20695555555, and that's positive. So this is in terms of seconds.
I didn't include
Obviously, the other number would be a little bit different.
I didn't include the 10 in the divided by 32, so
I didn't get that.
10.
What do you mean?
What'd you get?
Did you put the whole top in parentheses?
No.
That's probably what you're wrong.
10 minus.
Silly dog.
How much was
Two.
it?
You got 2 minus. Yeah.
This is
Plus or minus.
Gosh, 2 and a plus minus.
Yeah.
2 good job.
Well, not really.
Okay, so as you're typing that in, so it's 2.2
Who did your hair?
seconds roughly.
I did it.
All right, and it
I
worked.
didn't get that either.
The hotel.
Are you doing plus 10 or minus 10? Did you divide by negative 32?
See, I did that
Yes.
in Jamaica when my hair was kind of long.
Oh, wait.
And I did that whole my whole head and it took me 3.5 hours.
What'd you get, Brody?
Yeah.
We stopped there for 2 hours for her to get it.
It's a secret. Well, obviously.
Didn't take too long.
I don't. Is anyone not getting my number that I'm coming up with?
I
Other than
you.
Brody?
I got it.
Can I have a bathroom?
I got that
All
one.
right, you got that.
I'm not.
All right. Okay. All right. Last thing here.
Yeah.
Okay. All right. Last thing. Velocity. Negative 32. We're gonna take it times 2.2 and then subtract 10.
Divided by negative 50.
Oh, I.
Negative-
It's already crusty enough.
Negative 32 times 2.2, and then we subtract 10 more. So it's going to hit with a velocity of 80.4.
Sweet.
So 80.4, and that's feet per second.
Minus 10.
Isaac's more faster than that.
Velocity.
Yep.
I mean, it's a negative number. I mean, Isaac's definitely more faster than that. All fast.
All right. Questions at all about what we did here?
No, sir.
No say.
Okay, that's it for today.
No, I.
Big words.